So sorry for those of you at home, I started teaching and forgot to hit record, but just to let you know, we're looking at roller coaster loops. I'm not going to ask you a question this tough on the test. You'll see why. So we have a roller coaster that barely makes it around a vertical loop of 4 meters. And the first question it asks is find the minimum height that the roller coaster needs to start from at the top of the hill. We analyzed this. We decided to let initial be here, final be here. Diego said there's a change in height, there's a change in speed, there's yucky curvy path. It's conservation of energy. We said we're starting at rest, and we started to fill in the rest of the equation. So potential energy initial is mgh initial, kinetic energy final is a half mv final. Don't forget the squared, Mr. Dewick. Plus mgh final. Hey, folks, can little kids and grown-ups go on this roller coaster? Okay. I want to get H initial by itself. Eventually, I'm going to divide by G, but let's look on the right-hand side here. Do I know the final height? Well, sort of. How far from here to here? What do I call that distance? What letter have I used for the distance from the center to the edge of the circle? Radius, R, yes? So, do a little thought puzzle. How far from here to here? R, yes? I'm going to do this without numbers. I know it's 4, but I'm going to do this algebraically. How far from here to here? R. How far from here to here? How far from here to here? So what's the total height? Not R. 2R. So in my next line, I'm going to write GH initial equals a half V final squared plus G 2R. Do I know G? 9.8. Do I know the speed at the top of the loop? No. But maybe we can figure it out. At the top of the loop, what path are we tracing out? This is a job for a free body diagram. What are the forces at the top of the loop? Get the obvious one. What else? Which way? Whichever way the head is pointing. So there is a normal force, but look at example 1. What word did I underline? What that means is the normal force is 0 because we're barely making it over. We have no extra force to spare. You would feel like you were about to fall out of your chair. You're not. If we go slower, the coaster will fall off the track. If we go faster, you would feel like you were getting pushed into the chair just a little because you would feel a normal force pushing out on you. Okay? So normal force is 0. Who's winning? Who's losing? It's a trick question. No one. So here's what we have at the top. mg equals mv squared over r. And I'm going to use the v squared over r because I want to find an expression for v. Actually, I want to find an expression for v squared because there's a v squared here. Oh, m's cancel. So normally v would be the square root of g, but I don't want to do the square root thing. I think v squared is just g. So that can go right there. Here's what I'm going to get. GH initial equals 0.5 g plus 2 g. Oh. What? What? So what does that mean? That means that this roller coaster would work on Mars's gravity or on the moon's gravity. This hill would still get you through the loop. Your speeds would be different. You'd be traveling way slower on the moon because there's a smaller acceleration, but you would still make it through the loop. Okay? Not only that, here's what I end up with then. My initial height is 0.5r plus 2r. Aren't those like terms? What is 0.5r plus 2r? Elias, you're right. 2.5 R. I'm going to say I like this question. I'm not going to say I like this question, like this question, like this question. Here's what I love about this question. First of all, it's a roller coaster loop. But I love that. Look at all the writing that we've done, and we end up with this. Your initial height just has to be 2.5 times the radius of the loop. I'm willing to bet that ride designers, in the same way that you've all memorized F equals what MA, I'm willing to bet that's probably something that a ride designer just has kind of in their back pocket. How high does the initial hill have to be? Minimum, if you're starting from rest, got to be 2.5 times the radius of your roller coaster loop. Otherwise, you're not making it through. Oh, add some extra safety margin, so don't make it exactly 2.5 times higher. Make it 3 times or 4 times higher, but got to be at least that. And now we can actually plug it. So here's kind of our little handy-dandy reference, but now we can actually plug it in. H initial is going to be 2.5 times 4. I think I can do that in my head, because 2 times 4 is... Anyone? 2 times 4 is 8, and 0.5 times 4 is 2. I think it's 10. Okay? So this is one of my favorite questions, just because look at all the writing that we did. I mean, conservation of energy, circular motion, free body diagram, 2.5 times the radius. I love it when stuff cancels and comes together like that. My little math nerd heart goes, ooh, that's an elegant solution, is the phrase we use in math. We call it elegant. Okay. What did B want me to find? What did B want me to find? Where? Where? Okay, so now I'm going to redo this, but now final is going to be at the bottom of the loop. There's still a change in height, change in speed, yucky curvy path. Well, first of all, what do they want me to find? Normal force. Let's do a free body diagram for the bottom. What are the forces at the bottom? Get the obvious one. Gravity. Bigger, smaller, or the same size as mg? What path are we tracing out? We're still part of that circle, so at the bottom, we would have this. Normal force minus mg equals mv squared over r. At the bottom, the normal force is going to be mg plus mv squared over r. This is not a swappy dance one. We're getting the normal force by itself. Okay. I know G. I know R. I don't know V at the bottom. Well, is there a change in height? Is there a change in speed? Is there a yucky curvy path? I think I can find V, so I'll make a little note here. Need V. We can find it with conservation of energy. Okay? So it's going to be kinetic initial plus potential initial equals kinetic final plus potential final. This one's a little bit nicer because we're starting at rest, and now we are on the ground, so I can cancel out potential energy final. I get this. mgh initial equals a half mv final squared. Are we still in the world of little kids and grown-ups? Yep. How would I get the v by itself? Oh, I'm not going to get the v by itself. Since it's a v squared over here, I'm going to get the v squared by itself and just save myself a little bit of work. I think I'm going to get this. V squared, v final squared, v at the bottom squared, equals 2g h initial. But wait. What did I write for h initial in the box? V squared equals 2g 2.5r. Let's look at the 2 and the 2.5, the numbers. What is 2 times 2.5? 5 GR. How fast are you traveling at the bottom? 5 GR. Let's plug that into here, and we're going to get a normal force of mg plus m5 GR over r. Ooh, in that second fraction, the r's will cancel. And so I end up with a normal force of mg plus 5 mg. Is that okay? Aren't those like terms? What is 1 mg plus 5 mg? Do I know m? It's going to be 6 times 50 times 9.8, which is what? What was the mass 50? I can't remember. Was it 50? Yep. 2,900. Even? 29. I missed that last digit every time. 4. I couldn't hear the 4. Sorry. And that is newtons, Mr. Duke. What's your normal? mg? What normal is this person experiencing? What's your normal? 1 mg, right? Oh, I accidentally erased the g. What normal is this person experiencing? So part C, how many g's are they pulling? Which is well beyond comfort level. So this is why you've never seen been on a roller coaster loop that's a circle. The first couple that they built were, as I understand the history, the first loop on a roller coaster track was built at Coney Island around 1905 in New York. And it wasn't what we would think of as a roller coaster. It was just a straight downhill ramp with a loop at the end. So you climbed stairs to the top of the platform, you got on sort of like a mining car, and you went zipping down, and it was a circular loop. And you were pulling more than 6 Gs, because 6 Gs was bare minimum. You better believe their height was well more than 2.5 times the radius. And they had to have nurses and doctors and ambulances stationed at the bottom of the ride. But it was 1905. People loved it. They went on it. They thought it was great. Like, oh, Whiplash, how are you doing? Oh, I bruised my elbow pretty bad. And I had kind of blacked out for a while. It was so much fun. Okay. Then for the longest time, they didn't do loops. And then in I think it was 71, Six Flags Magic Mountain did the first roller coaster loop, multi-loop coaster. I've been on it. But it doesn't look like what you think of as the loop. In fact, all roller coaster loops are what are called a clothoid loop. And a clothoid loop looks like this. Almost teardrop shaped. If you want the fancy math definition, it is a loop where the radius is constantly decreasing. And so what you end up doing is when you hit the loop, you slow down, you slow down, you slow down, you kind of make it through the top, but pretty slow. And then you speed up, you speed up, you speed up, and you make it your way through. If you look at a roller coaster loop from the side, the more the loop looks like a circle, the more G's you're going to pull at the bottom. The more it looks like that, the more, it'll be fun. How many of you have been on California Screaming, or what's now called the Incredi Coaster? Okay, that loop, if you look at it from the side, looks very circular. You're pulling some pretty good G's at the bottom. I've been on that coaster many times. And so what I like to do when I'm about to hit the bottom of the loop is I'll either hold my arms straight out and then just try doing this against the G's, or I'll lean forward in my shoulder restraints, and then at the bottom I'll just try and lift my head straight up, and I can't. Okay, so I got to have some fun with it that way. So absolutely, you would not build a loop that was circular. You're pulling at least 6 Gs. Put your pencils down, look up. Oh, what did I call the video, Mr. Duke? Oh, 5th gear.
Welcome back. Right, I'm really excited about this next item because it's the biggest and bestest thing 5th gear has ever done.
Hell yeah, check this out. Who remembers these? Hot Wheels Loop the Loop. Go on, Tom, send one down.
There we go.
Yes, but what we wanted to know is, could you do that in a real-life, family-sized car?
Yeah, we gave the job to our friendly neighbourhood stuntman, Steve Trulia, but we wanted some questions answering first. How fast would he have to go? Would the car stick to the road? And would he black out under the G-forces?
Steve Trulia is the man facing this monster challenge. As 5th gear's head of danger, he's rolled, crashed and crashed again in numerous 5th gear stunts. But even by these extreme standards, nothing can prepare him for our most dangerous stunt yet. Clearly, scaling a toy up to a record-breaking 40 feet high using 5 tons of steel and a real-life motor was going to be dangerous. So we sent Steve to Cambridge University's Dr. Hugh Hunt to find out how fast he'd have to go. Now listen carefully.
2R plus a half V in squared.
That looks kind of familiar.
Starting to cook my brain a bit now.
36 miles per hour.
36 miles an hour.
But you know what we haven't worked out though? Is what are the G-forces you're going to experience? Because you want to know whether you're going to black out or not. The total G-force you will experience as you enter this loop will be 6.
We calculated that. We could have done this.
G.
Nice.
A bit more confidence.
In fact, if you look behind him, that looks fairly similar to what we just did, I think.
Because of the science, but at the end of the day, I don't know if that's going to count when I'm staring at the track with my foot in the accelerator.
To lessen the chances of Steve blacking out at the wheel, he needed to get used to pulling 6G. The only place to do that was in this.
Here we go into the loop.
So pilots pull some pretty impressive Gs as well, right?
Stunt day. The day 5th gear finds out if you really can drive a car around a 40-foot high loop-the-loop. If successful, stuntman Steve Trulia will set a new world record. If he fails and falls out of the loop, the massive deceleration forces as he hits the ground could be fatal. The entry speed is therefore literally a matter of life or death, so Steve verified the car's speedo with GPS
36, 37.
and then checked again with a calibrated radar gun. 36 miles an hour had been calculated as the ideal entry speed. Slower than this and he'd fall. Much faster and the G-forces would knock him unconscious and exert a dangerous force on the ramp structure.
So that's the other argument. Why does it just go really, really fast? More Gs and also hard on the ramp structure. So he's got to nail this.
The Toyota Aygo Steve had chosen for the stunt had been heavily modified to make it strong enough and hopefully safe enough should things go wrong.
Something almost does go very wrong. See if you can spot it.
Here we go. This is it. This is it. Oh, going in too far. Here we go.
Can you see it? They didn't beef the suspension of the car up enough, and so the Gs were enough that the bumper is dragging. What will the bumper dragging do to your speed? It is going to slow it down. Now, either he was watching his speedometer and adjusting on the fly, or they lucked out and had a little bit of a safety margin.
I really thought I'd lost it. I felt weightless. I thought, I'm falling. I'm so glad that's where we touched the road all the way around. As soon as I left the ramp, just a complete feeling of joy and elation.
Dr. Hugh Hunt's analysis revealed how close we'd come to disaster. Just 2.5 miles an hour slower and Steve would have fallen.
And here we go.
1 mile an hour faster and the extra
You can see the bumper already starting to drag.
friction caused by the scraping would have made him fall as well. Steve hit it spot on, so take a moment to savour the world record for driving a car around the largest loop-the-loop. Chances are you'll never see it executed so perfectly ever again.
Okay, well, what if instead of a loop-the-loop, what if you were in a tunnel going really fast? Could you do a quick loop on the fly? Well, it's a good question.
You would be amazed how often I get asked that question. So, to get an answer, I've come to the network of sewage tunnels underneath Belfast, and obviously, for the next few minutes, we've asked people in the city to cross their legs. Oh, God. Oh dear, it's splashing. I've considered the diameter of the tunnel, the car's centre of gravity, everything, and I've worked out the precise speed I need to be going is 17.5 metres per second. I just wish I knew what that was in miles an hour, because that's what I'm getting on the speedway. I think it's about 37 miles an hour, there we are, it's roughly there, and here we go.
Something almost goes horribly wrong here as well.
Building it up. If this goes wrong, I really am in a world of Here we go! There you are, Mr. Needham. If you're looking to drive upside down through the tunnels of Belfast, Twingo 133, absolutely ideal.
So that was pretty close. What's your homework? I'm not going to assign anything from here. Instead, I'm going to be giving you a take-home quiz and the big ultimate review study guide for this unit. Is to take a look at the take-home quiz, please. Quiz 1. The one-page piece of paper. I notice in number 1, I've given you the plane's speed. Oh, it says an airplane turns a horizontal circle in 2 minutes. All of you, of course, would cross out the 2 minutes and change that to seconds, yes? I'll let you figure out how to do that. If the plane's speed is 170 meters per second, what's the radius? I think here, for this one, you're going to use the circular speed equation, which is on your sheet. I'm not going to tell it to you. I want you to get used to finding them. Then B, to find the centripetal acceleration, well, once you know the speed and the radius, then I think you'll use v squared over r to find the acceleration. So no free body diagram or anything for number 1. No free body diagram for number 2, because number 2 says what centripetal force is needed to keep a 12 kilogram object revolving with a period of 0.2 seconds and a radius of 6 meters. This is like when I ask you for the net force, no free body diagram, just plug and chug. Number 3 wants you to find the centripetal acceleration. No free body diagram required there either. Find the acceleration. I either gave you the speed or the period. I can't remember, but I gave you one of those. Ferris wheel. Now you're going to need to do a free body diagram. So A wants the force that the bench exerts at the top of the Ferris wheel. It really wants you to find the normal force. B wants the force at the bottom of the Ferris wheel. They won't be the same. One of them will be bigger than your normal. One of them will be smaller than your normal. Turn the page over. So Even though in real life we never build circular roller coaster loops, that's the physics we can handle, so we're going to look at circular roller coaster loops. At the top of a circular roller coaster loop of radius 11 meters, a 75 kilogram rider experiences a normal force of 4.5 times their weight. How fast is the coaster traveling? I haven't blatantly done one like this with you. I've done it in separate chunks, so I'm doing this on purpose to see if you can have the aha moment yourself. B, at the bottom, after the first loop, the riders hit a second loop. At the top of the second loop, the rider is traveling at 16 meters per second and they feel a normal force of twice their weight. What's the radius of the second loop? So here I gave you the radius and said, how fast? Here I gave you how fast and said, tell me the radius. Okay. It's going to be a similar setup, I think. Can you all look at the ultimate circular motion review? We're going to cross off some questions. Okay. I like number 1 is good. You can circle 1. Circle 2. You can cross out number 3. You can cross out number 4, number 5, If you're wondering why there's some numbers missing, I used to do circular motion and gravity in the same unit. When you look at my online answer key, the answer key showing all my steps will have all the questions, so you will see a solution for number 4 and number 5, and just skip to number 8 if you're stuck, okay? Number 8, circle that one. That one's good. You can cross out number 9. Cross out number 10. 14 is good. You can cross out 15. 16 is good. 17 is good. Sorry, 20 is good. I said 17. 20 is good. You can cross out 21. You can cross out 22. The Gravitron, 27 is good. 28 is good. You can cross out 32. 33 is good. You can cross out 34. 35 is good. But you can cross out 39. You can cross out 40. The rope at an angle like 39 and 40, that was also part of cool applications because we would analyze the wave swinger or those little toy planes that go around in a circle. Anyways, not going to do that. 41 is good. 44 and 45 are both good. 46 is good. And then there's the answers, but also I'll post a full showing all my steps answer key as well.